Morning, guys.
Morning, guys.
We're going to talk about Le Châtelier today. So
LeChatliers.
we're going to spend a little time in France. Henri Louis LeChatlier. Yeah. Okay, so there's a picture of the gentleman. He's a French chemist who, in or about 1884, if stress is applied to a system at equilibrium, it will shift in one direction that relieves this stress.
Okay.
And we kind of have already learned about that a little bit through Q, right?
Right.
But Henri Louis talks about it conceptually instead of mathematically.
That is true.
Right. So that makes it a little bit easier to deal with.
No calculator required for this section, Mr. Kane, at all?
We might make you calculate a KEQ or determine, but actually we probably won't.
For LeChatlier.
I mean, if you want to prove something to yourself with some mathematics, you can.
Okay.
But otherwise, no, you don't really need to do math. This should be purely conceptual. He defines a stress as any change that upsets the equilibrium.
So this guy actually had systems at equilibrium. Going along, turning along, cycle, and he goes and messes with it, basically. Correct?
Right,
He screws it all up.
And he sees what happens.
Okay. All right, so a stress is anything that's going to upset the cart, the apple cart. Oh,
right.
I got an analogy.
And as we learned with our review of what affects a reaction rates, changes in concentration, pressure, volume, and temperature are all going to affect a chemical reaction.
Okay.
So those are going to be the stresses that we use in our LeChatelier's principle.
Concentrations first. All right.
All right, so we start with this reaction, this hypothetical reaction that you can see has A and B as reactants and C and D as products,
Right.
and there is molar ratios written down there. We say that an increase in concentration of any substance is going to shift away from that increase. So if I added more B, the reaction is going to have lots of extra B, so it's going to try and make C and D.
Right, so shift to the right.
But if I added a lot more C to the reaction is going to want to get rid of that C.
So it's going to shift to the left.
So it's going to shift to the left.
Well, that's easy.
Right? Okay. A decrease in concentration of any substance is going to shift towards that decrease.
All right.
So let's
fill the hole, yeah?
Yeah. Let's say I stuck my hand in there and I took C out.
All
The
right.
reaction's going to want to shift to the right to try and replace the C that I took out.
All right.
Or if I stuck my hand in there and took out A, it's going to try and shift to the left and try and replace that A that I took.
So it's going to try and reestablish equilibrium.
Correct. It's going to
All
try
right.
and reestablish equilibrium. It's going to try and reestablish the previous concentrations,
All right.
the ratios. Okay. So some examples of concentration. For example, if I add some CO,
gonna
some
shift
carbon
to the
monoxide.
right.
Yep, it's CO's on the left, so it's going to try and shift to the right in order to compensate for that.
Yep.
All right. If we take out some water, it's going to try and replace that water, right?
So it's going to shift to the right.
So it's going to shift to the right again.
Also going to shift to the right. All right.
If we take out some carbon monoxide, though, it's going to try and replace it.
So it's going to shift to the left.
Shift to the left. Is this getting easy?
Yeah, this is easy.
All right. This is very purely conceptual. If we add some water, now it's going to have too much water.
So it's going to shift to the left also.
Right. It's going to try and get rid of the water. So it's going to shift to the left, make more carbon monoxide and more hydrogen gas.
Concentration, easy.
Concentration's pretty simple.
Yep.
Changes in volume.
Ooh, volume's only going to affect gases.
Right, because gases are the ones that really want the space.
Yeah.
Right. So decrease, this is viewed through a couple of ways. Some people like to view it through volume, some people like to view it through pressure.
Volume and pressure are opposite to each other.
Right, 'cause
so whatever you do to volume is opposite, will have the opposite effect on pressure.
Right, because I like to think about it as a balloon.
Okay.
You blow up a balloon and you tie it off.
Uh-huh.
And if you push on the balloon, you're decreasing the volume, right?
Correct.
But you're also increasing the pressure.
Right, because there's less space for the gas particles to be in.
So decreased volume, increased pressure.
Okay, so
right?
opposites.
So
They're
opposites. They're opposites. Okay. Now, ultimately, what happens here is that the reaction wants to shift to the side that has less gas molecules. Because if you decrease the volume, it's got less space to be in. So it's going to want less gas molecules. So what you do is you add up the gas molecules on both sides, figure out which side has less, and that's the direction it goes.
Yep.
Let's see if we can do this. So we got to add up our gas molecules. It looks like they're all gases, right?
Yep,
So
homogeneous
I've
reaction.
got 4 gas molecules over here. 1 gas molecule plus 3 gas molecule. And I've got 2 over here, so it's homogeneous.
Right, and you're decreasing volume, which is going to increase pressure and increase concentration, because pressure and concentration go hand in hand.
Right.
Especially if they're all at the same temperature.
So if I've got less space, it's going to want to be on the side with only 2 moles of a gas rather than 4 moles.
Correct.
Right.
So you are going to shift to the right.
Right. So we're going to go to the right. However,
the opposite to that.
Right. If I do the opposite, if I increase the volume instead, it's going to want to be on the side that has more space. It's going to kind of relax.
Because increasing the volume will decrease the pressure, aka concentration. And if you decrease the concentration, you're going to want to make more fast. So you'll be shifting to the left.
Correct. And that's what we show here.
Yep. That's easy.
Okay. Changes in temperature. It's the only way to change the KEQ.
Only way to change the value, yes. Of
change
KEQ.
the value of the
yes.
KEQ, right?
Yes. Now, the problem with this is you got to decide which side energy is on. If you're increasing temperature, you're going to shift away from the side that the word energy is written on.
Right. You can think of energy as a concentration
Correct.
also.
Consider it, you can treat it like it's one of the substances in the reaction.
Because excess energy is going to make the reaction want to get rid of the energy.
Correct.
So it's going to shift away from that side.
Yes, and if you're decreasing temperature, you're decreasing energy, so you're going to shift toward the side where the word energy is written in the reaction.
Because the reaction is going to try and make that energy up.
Yep.
Right?
That is correct.
Okay.
Now, this is the only one that's going to actually change the value of K. If you're shifting toward the product side, you are going to make more products. Your K is going to get bigger. Correct?
Correct. And if you shift towards the left, then it's going to be getting
smaller because your products are getting smaller.
Right, and that should make sense because of what K means.
Yes. All right, so here's an example.
Right.
Notice energy or heat written on the right-hand side.
Right.
Treat it like a substance.
So treat it like a substance. So if I was to add more heat, the reaction's going to want to get rid of it because it's got excess heat.
Correct. So it's going to shift to the left.
Shift to the left. And that will affect the KEQ. It will actually make the KEQ drop because we're shifting to the left.
We're shifting to the left, away from the products, making less products, more reactants, less products, smaller KEQ.
If I take heat away, on the other hand, if I cool it down, notice the little blue.
Okay, cooling down. Oh, that's cute.
Yeah, it's going to try and make up more heat.
So it's shifting to the right.
So it's going to shift to the right, and what that's going to do, more products means
higher KEQ.
Higher KEQs.
All right.
Right.
Heat can be on either side?
Yeah, heat can be on the either side. We haven't discussed this yet, but there's two kinds of reactions called exothermic and endothermic.
Yeah.
This is an endothermic reaction. But if I take away heat from this kind of a reaction where heat is written on this side, it's going to try and replace it also.
This concept's the same. It's going to go towards it to replace the whole.
Yeah, so it's going to shift to the left because heat happens to be on the left side.
Yeah, so if you're shifting away from the products, you're making less products, the KEQ is going to go down.
Yep, and the KEQ goes down because you're shifting left.
Okay.
Yeah, just like you said.
So if we give them the word heat or energy, this is real simple.
Yeah, just treat it like a concentration of any other substance. So if we were to actually increase the amount of heat,
and heat's found on the left-hand side, so if you're increasing the energy, increasing the heat, it's going to shift away from that increase.
So it's going
to shift to the right, and you're going to make more products, and your KEQ is going to go up. Oh, exactly. This is simple.
Yep.
Easy peasy.
Okay, one final example.
Ooh, I'm scared.
Check this out. It's a heterogeneous reaction.
Oh.
All right. Oh,
this is going to be all of them, huh?
If we increase B.
Nothing. It is not written in the equilibrium expression because it is a pure solid of a heterogeneous reaction. It changes in concentration, but not enough to shift the equilibrium.
Right.
Okay.
Solids and liquids don't affect the KEQ, so since it's heterogeneous, we don't think about it.
Because if we were to write the expression, it would just be C, the concentration of C over the concentration of A.
Just like that.
Yep. All right, increased pressure. Okay, this one's tough.
We got to consider only the gas molecules, right?
And it's a one.
It's one molecule.
1-to-1 ratio.
So if it's a 1-to-1 ratio, which side wins?
Neither. It's a tie. So nothing.
So no shift?
Yeah, no shift.
All right, no shift. Because there's an equal number of moles on each side.
It'll affect them both equally.
All right. What about decreasing the temperature?
Okay, heat is written on the left. You're going to treat it like it's one of the substances, treat it like the concentration concept. If you're decreasing the temperature, you're decreasing the energy, decreasing the heat. That means it's going to shift to the left to fill the void, fill the hole.
Right, shifts to the left.
So when it shifts to the left, it's shifting away from the products, making less products. Therefore, KEQ goes down.
Which means KEQ is going to decrease.
That's the only one that changes the value of K.
And then finally, what happens if we add a catalyst?
Nothing.
Yeah,
Absolutely nothing.
No shift. It changes the rates, but it doesn't change the actual KEQ where the reaction wants to finally settle.
That was it. That it?
That's it.
That's it on Le Châtelier. Bye.